Next slide. With over 5,000 exoplanets in nearly 3,800 planetary systems discovered so far, and thousands of others still to be confirmed in our data processing queue, what have we found about the properties of planetary systems in this part of the galaxy? The left set of figures summarizes the orbit sizes of the exoplanets with known orbit sizes and masses. The top left figure is for the exoplanets with masses greater than 0.5 times Jupiter's mass, and the bottom left figure is for the less massive exoplanets. Note that the low-mass exoplanets farther from their star are going to be much harder to detect with our current techniques, so the bars for the larger orbits are very likely shorter than they should be. That is, there are probably more small exoplanets far from their star than we can see. The right figure above is for the exoplanets with known eccentricities. Most of these exoplanets with known orbit eccentricities are Saturn-Jupiter mass, or larger, and most of those that transit their star have densities like Saturn-Jupiter, or less. The next plot is the mass of the planets plotted versus their orbital period. As of late June 2022, the Earth mass planets orbiting at a decent distance from their star is shown with the green box at center bottom. Again, remember that small exoplanets orbiting farther from their parent star are very hard to find using our current technology. You can select the links for the updated graphs. Two things to notice are how close the large exoplanets, those with 50% Jupiter's mass or larger, how close the large exoplanets are to their stars, and the large eccentricities of some of the exoplanet orbits. The large exoplanets very close to their stars, within half of an astronomical unit, are called hot Jupiters because their temperatures can get up to 1,000 degrees centigrade in their cloud tops. The clouds would probably be made out of rock dust minerals instead of the ammonia, ammonium hydrosulfide, and water clouds of the much colder Jupiter and Saturn. The hot Jupiters with low densities have atmospheres puffed out by the extreme solar heating. That inflates their diameter. One puzzling statistic from the Kepler mission has to do with the sizes, diameters, of the exoplanets. More than 3/4 of the planet candidates in the Kepler catalog have sizes ranging between that of the Earth and Neptune. Why does not our solar system have a planet in that size range? In that respect, our solar system's architecture seems to be an unusual one in the galaxy. Further refinement of the condensation model will need to be made to explain why super-Earths, mini-Neptunes, are so common, and what happened in our solar system to prevent such a planet from forming or continue to exist in our solar system. One possibility is that there is, in fact, a mini-Neptune orbiting very far from the Sun that hasn't been found yet. Let's take another look at the hot Jupiters. This picture compares a normal or expected Jovian-type planet on the left with a surprising hot Jupiter type on the right. The hot Jupiters are much closer to their star than Mercury is to our Sun, so the hot Jupiters are much hotter than Mercury. Their high temperatures make them puffier than a normal Jupiter type, so their average densities are lower than normal Jupiters. So here's a repeat of the picture we saw when looking at the condensation model for the formation of our solar system. The large Jovian planets are supposed to form beyond the frost line, where hydrogen compounds such as water, ammonia, and methane, etc., can freeze out and form larger cores than what a rock iron terrestrial planet can, because there's more hydrogen compounds than rock and metal in the planetary disk. Those Jovian cores can get big enough to then suck up a lot of the surrounding hydrogen and helium in the nebula to get really large. So, why do we find some planetary systems with a Jovian planet even closer than Mercury is to the Sun? Over a decade before the discovery of the first exoplanets, astronomers predicted as part of the condensation model that large gas rock clumps would form far from a young star and spiral inward toward the star because of friction with the gas remaining in the disk around the forming star. The gas rock clumps can also interact with each other, sending one into a small orbit while the other is ejected out of the system. Such interactions may also explain the elliptical orbits we see. Some astronomers working on planet formation models are looking for ways to halt the inward spiral of the gas giant planets near the star through tidal interactions between the planet and star. Perhaps the gas giant planets we see are simply the ones that did not have time to spiral completely into the stars before the gas disk was cleared away by the strong T-Tauri winds that accompany the start of nuclear fusion in the star. Perhaps in our solar system, other giant planets had formed but did not survive or were ejected. Evidence for the ejection possibility comes from the potentially large number of free floater planets that the microlens surveys are saying must exist in the galaxy. Recent computer simulations of the dynamical history of our solar system show that the gravity of Saturn helped prevent Jupiter from spiraling into the Sun, and that their orbits may have started further out than they are now, then moved closer in than they are now, and then finally moved further out to their present distances. The simulations also show that Uranus's initial orbit might have been larger than Neptune's initial orbit, and that both planets' orbits were smaller than they are now. This shuffling of the gas giant planets would also have affected the material forming the terrestrial planets and changed the distributions of various types of asteroids and comets. The Kepler mission has provided strong evidence in favor of the inward migration idea for how the hot Jupiter systems formed. A 2012 study looked at over 60 hot Jupiter systems in the Kepler catalog, and none of them had multiple planets, while other systems with large planets further out can have multiple planets. Observations of other star planet formation places and other planetary systems, along with more sophisticated computer simulations, have confirmed various features of the condensation model, and they have also led to modifications and extensions of the theory in the continual interaction of the observation, theory, testing, error correction process of science. Is our neat, orderly solar system unusual? The answer to that question has implications to how likely extraterrestrial life is going to exist in other parts of the galaxy. If a planetary system like ours is needed for life to arise on at least one of the planets, and if a planetary system like ours is unusual, then habitable Earth-sized planets in the habitable zone of their star may be rare, and extraterrestrial life is going to be rare or even non-existent. If a planetary system like ours is not unusual, or life could arise in a planetary system really different from ours, then Earth-sized planets in the habitable zone of their star may be common, and extraterrestrial life could be found in lots of places, and maybe even some planets might have civilizations with whom we could communicate.